Testing. Good. Do you want to check the audio level? Testing, testing. Yeah, great. Okay. Thank you, Richard. Great. Okay, good morning, everyone. I think we'll try to get started, if you guys want to. Okay. Carol, Deb, we're going to get started. Richard, can you close the door in the back? Thanks. Great. Great. So we're going to transition today from the Maxwell's equations world back to the Boltzmann world and back to radiative transport. And that will be the predominant theme for the rest of the course. And today we'll focus mostly on analytical methods, how we can, the techniques one can use to derive analytical approximations to the radiative transport equation. And we'll discuss those and their strengths and their limitations. And then I'll show you a series of results from a couple of these analytical approximations and compare them to Monte Carlo simulations of the same situation, so we can appreciate, like I said, the power of these approximations as well as their limitations. The results I'll show you will focus more on internal light fields. We had chatted on the first day about their different considerations for treating light transport when you're interested in dosimetry or in fluorescence excitation versus diagnostics. And Thursday and Friday we'll focus more on the diagnostic signals. Today we're going to focus more on the internal signals. Even though one may ultimately need to use a more general or powerful solver such as Monte Carlo to do accurate dosimetry in a complex system with multiple tissue types, complex geometries, I still believe that analytical approximations enable you to do very quick back-of-the-envelope calculations for feasibility for various applications, whether it be dosimetry or for fluorescence excitation. I hope that the results in this talk will give you some tools you can use to do some quick and fast approximations, which I think is really helpful kind of in day-to-day practice. And then I'll end talking about internal light fields, not only in kind of what we call semi-infinite tissues, but also in tissue slabs, because we're going to transition to the next talk where we start to deal with diagnostics by how one can obtain optical properties from measurements of thin sections of tissue, both reflectance and transmission. And these were the first methods really developed back in the 80s for first trying to estimate what are the optical scattering and absorption properties of tissue. And that's by excising the tissue, by making reflectance and transmittance measurements, and then coupling that with some sort of radiative transport solver to actually figure out those optical properties. And so I'm going to show some results from there, but then the next talk given by Dr. Rolf Sager will go into that method in detail, because that's actually what you're going to be doing in lab today. Actually, you're going to be making some measurements on what's called integrating sphere systems of reflectance and transmittance on primarily tissue phantoms, not real tissue. And then you'll be using software to process that data to try to extract the optical properties, both on sample data sets that we've pre-acquired for you, as well as data sets that you'll be acquiring. And hopefully, again, the strengths and limitations of those methods will give you more insight as well into what the capabilities are with respect to extracting optical properties from such measurements. Okay. So before I get started, are there any questions? Okay. From yesterday. Good. So as far as our outline and teaching objectives, I'm going to introduce two different analytical approximations, one of which is actually broadly used in the field of biomedical optics, one that's definitely documented in the literature, but I don't think as pervasive. So the first is kind of the standard diffusion approximation, and then we're going to talk about a variant of that approximation called the delta P1 approximation, and we'll learn how these approximations are derived from the radiative transport equation and their underlying assumptions and limitations. These approximations will transform this very complex integral differential equation, which is the RTE, into a partial differential equation, which, while not trivial to solve, is much easier to solve than the RTE analytically. Now, once you have this governing equation, those of you who are familiar with solving differential equations, you know that you have to have boundary conditions in order to solve these equations. And so we'll talk about how we can formulate these boundary conditions in typical situations where you have a refractive index mismatch between your tissue and the surrounding media in which you're making the measurement. So we'll show how these are formulated, not only in the standard diffusion approximation, but also I'll provide at least one slide on how such boundary conditions are handled in a Monte Carlo simulation as well. Now, with that, I'll give you some very basic solutions, but I'll show mostly results. And so I want to talk about how the configuration of your source affects the depth to which light travels within the tissue. And this is really critical for dosimetry or for fluorescence excitation. At some point, you need to understand how do optical properties, how do the sizes of your beam impact your ability to deliver light to targeted locations in tissue. And I'll develop some metrics actually for optical depth, which I think will be important and I think is novel in some ways. And then we'll kind of go into a detailed kind of set of case studies where we examine the impact of the refractive index mismatch between tissue and the surrounding material, as well as optical properties on this internal fluence rate distribution in turbid tissues. We'll also look at the impact of beam diameter. So first we'll look at kind of planar solutions where you have a broad beam, a one-dimensional case, and you just look at penetration in Z. We'll also look at how constraining that beam to finite beam sizes impacts this distribution. And then we'll end with radiative transport in slabs and look at how slab thickness and optical properties affect not only the fluence rate distribution inside, but also the reflectance, absorbance, and transmittance. Okay? So we've got actually a lot to go through, but hopefully we'll keep people engaged. So I just want to start with one slide that we had from last time, which is the radiative transport equation, just to remind you that this will be our starting point. So on the left-hand side, I've gathered the two terms that talk about local changes in the fluence, in the radiance, L, which again is this six-dimensional object which varies both with space, three dimensions in space, 2 dimensions in direction, and 1 dimension in time. This first term is the local rate of change in time, and this second term is a directional derivative which is meant to communicate the spatial gradient in the radiance along the direction omega, which is the direction that one is considering. And these changes, this local change can be influenced by losses due to absorption or scattering. Absorption, again, will extinguish the light, where scattering will simply redistribute the light from the angle that you're considering, omega, to some other angle, omega prime. And this is a loss, so we have to subtract that. And then, of course, you can gain through scattering from other directions, omega prime, into the direction that you're considering, omega. And this is a probability density function called the single scattering phase function. You multiply that by the amount of light that's available at those other angles that can scatter into omega. You integrate that over all possible angles omega prime and multiply it by the density of scattering you have in your material. So that's a gain. And then, of course, you can have gains from other sources. So mu t here is the sum of absorption and scattering because you have losses due to both, at least out of direction omega. And then, of course, mu s is just your single scattering coefficient. So any questions about this equation? Okay, so now we're going to kind of focus on how can we get this into a form that's easily solvable. Yes, Kayvon, we need the other microphone, please. Thank you. Kayvon?
So in the gain through scattering term,
yes,
that mu_s is like an overall mu_s for what you're looking at. It's not each individual mu_s at different.
Right. So remember, so there is a more general form of the radiative transport equation where mu_s can be a function of r. It can be a function of position, and so certainly you can do that. So there is a more generalizable form. I mean, of the equation where actually all the optical properties are varying in space. Okay. Thanks. Yeah. Certainly. Okay. Any other questions? Okay. So I'm first going to introduce what's known as the standard diffusion approximation. So the key challenge here, one way of simplifying this equation is to try and reduce the complexity inherent in the radiance, okay? And what we do is that we adopt a priori a functional form for the angular distribution of that radiance. And because the directions are described as vectors from the origin to the surface of a unit sphere, we can express this in terms of spherical harmonics generally. And the simplest way to do this is in using a system of Legendre polynomials, which are an infinite series of polynomials which a weighted sum can describe any function on a unit sphere. But the simplest approximation is to just truncate that series of Legendre polynomial at first order. And so what we're doing here is that we're going to substitute, we're going to say a priori we're going to allow the directional dependence of the radiance to be simplified or approximated by two terms. One term is just a scalar term that's independent of direction. And so that's what this green circle is meant to denote. So you're at some location R, which is this red dot, and the amount of light that you have emitting from that red dot is equal in all directions. So this is meant to actually denote a sphere, okay? And that intensity or that magnitude of the radiance, the isotropic term, is called the fluence rate. And then, because we know in reality there's going to be a net flow of light, you have a source, there are going to be regions where the density of light or the fluence rate is higher, and there'll be other locations where it's lower. You need to have some sort of directionality. And that is going to be contained in the first order term, which is simply a cosine variation. So J will be referred to as the flux. And this is a dot product of this flux vector with the direction of light. And so this is effectively gives you a cosine term. So graphically, what this is meant to do is to communicate a net flow of light in a directional sense. And so this cosine term, what it does is that so the direction of light is meant to indicate theta equals 0. And a cosine basically has positive contributions from 0 to 90 degrees, and then negative contributions from 90 degrees to 180, all the way to 270, and then becomes positive again from 270 to 360. So what this does is that this cosine term effectively pulls away or subtracts off some amount of this fluence rate in the backward hemisphere, but adds an additional amount of light in the forward hemisphere. And in doing so, it gives you this bias that you can have more light or less light as you want if you have a negative flux, but you have more light moving forward in this case than moving backward. And this gives you some sort of asymmetry or anisotropy in the radiance. So the net radiance is just basically a sphere plus a cosine theta term, and you can get some sort of net flow from regions of high fluence rate to low fluence rate. So this is a very simple approximation for this potentially very complex angular function, angular description of the radiance. And we do the same thing for this phase function, right? This phase function is also described on the unit sphere. We've talked about phase functions and how can be very, very structured. We saw phase functions describing Rayleigh scattering as well as Mie scattering. We've played around with them in the GUI yesterday. They can be very structured, as you've seen in the GUI exercise that you performed yesterday. We do a very similar approximation here. Again, you have an isotropic term here, which is just a constant, plus some anisotropic term. This is also a cosine theta term. G is the single scattering anisotropy. And I just want to mention that this 4 pi term in prefactor is just because this radiance is still power per unit cross-sectional area per unit steradian. And so the 4 pi basically is the normalization factor to get steradians back. Okay. Any questions on this? So just, okay, so what we do is that we take this equation for the radiance and this equation for the phase function, basically substitute it into this equation, and we do the appropriate integrations. You'll find that you'll end up having two partial differential equations, one that describes what is known as the fluence rate and one that describes the flux. And I won't show you the steps of doing that, but if people are interested, I can definitely give you references for that. And after substituting that, you get two partial differential equations, one that has both the fluence rate and the flux related to your source term. The source is also expressed in terms of an isotropic term plus a first order anisotropic term, because in general your source can have a complex angular configuration. And then you have another term, another equation that relates your flux with your fluence rate and Q1. And so you can actually then eliminate J from these equations. Here's some details here. And come out with this final partial differential equation. If some of you go into the literature, I just want to communicate that there is some inconsistencies in terminology depending on the literature you look at. And often in the classic radiative transport literature, especially in the nuclear field, even though we call this fluence or fluence rate, in that world they call this the flux. And in our world, we call this anisotropic term the flux. And in the nuclear world, they call it the current. So just word to the wise, in case you delve into the literature, you can get easily confused because flux may mean a different thing to some people than others. Okay. So we get this diffusion or P1 equation, and so essentially this looks like a diffusion equation in some ways, for those of you who may have experience in heat transfer or mass transfer. So we get a Laplacian term with respect to the fluence rate. This is a classic thing that comes in Laplacian or diffusion equations. Unlike diffusion equations, you have another term which is linear proportional with the fluence itself, and this is meant to communicate loss due to absorption. And the loss due to absorption doesn't only involve the absorption coefficient, but it also involves the transport coefficient, because the amount of absorption loss will depend on the amount of multiple scattering you have in the tissue. Because the absorption is linked to path length, and the amount of path length that these photons will travel within the tissue depends on scattering. And so it's not surprising that the degree of absorption loss considers both absorption and scattering. On the right-hand side, we have two terms that represent the flow of light. One is a second derivative with time, and this is similar to a term that arises in any wave propagation equation. If you remember from Jonica's lecture yesterday, he showed the wave equation for electric field, and there's this 1 over c squared partial derivative of the electric field, second partial derivative of electric field to the second derivative of time. So, so this is basically communicating a wave propagation. Interestingly, this prefactor communicates a non-physical velocity. It's actually the square root of this, the reciprocal of the square root of the reciprocal of this is meant to communicate the velocity, which would be the square root of 3 times the velocity of light, which is incorrect. And we'll see that when we look at solutions to the time domain form of this equation, I guess on Friday. We also have a term that's linked to a single derivative in time, which is typically the case in a diffusion equation. And then we also have a source term. So one thing I want to emphasize here is that, again, mu A is the absorption coefficient. Mu TR is the sum of the absorption and the reduced scattering coefficient, mu S prime, which we've discussed before. And the source term also has mu S prime and mu TR. So one thing you find is that even though we have the complete phase function in the radiative transport equation and the appearance of G in our phase function approximation, the resulting diffusion or P1 approximation does not have G appear by itself anywhere in this equation. G always appears parameterized within mu S prime. And what this means is that for a fixed value of the absorption coefficient, all pairs of mu S and G that produce identical values of mu S prime result in identical standard diffusion approximation solutions. So this means that the use of the standard diffusion approximation does not provide you any sensitivity to the moments of the phase function, which is one of its biggest limitations. Okay? And because we assume this relatively simplistic form of the radiance, this means that, especially in the presence of collimated light sources which display high directionality, in order for this approximation to kind of make sense intuitively, you're going to have, these photons really need to undergo multiple scattering events before this angular distribution of light is going to have this very mild asymmetric character. And so typically the assumptions that are made is that this is valid for values of the reduced scattering coefficient much larger than the absorption coefficient. So I believe there's a question here.
I was just kind of curious for the absorption loss.
Yeah.
If you multiply, or if you substituted mu TR for mu A and mu S, then you would have mu A squared, and that seems a little weird to me.
So mu TR is mu A plus mu S prime,
Yeah.
right? So you'll have
And the same with the source as well.
Yeah. So you'll have, and we'll look at this a little bit more. 3 times mu A. Right, so what is your question again with respect to this?
Well, if you multiply it out, then you would have mu A squared.
That's right. That's
and that
right.
seems a little bit weird to me because then the absorption would be loss.
Well, so what we're going to see is that when you solve this equation, you have a second derivative here. So actually the characteristic decay rate is actually the square root of this.
Oh, yeah.
Okay.
I remember that now.
Okay. Yeah.
Thank you.
Yeah, you're welcome. Okay, and we'll talk about that in a little bit. Okay, I'll just leave that up there. Okay, any other questions? Okay. So what I want to do now is just show you the form of the solution to the standard diffusion approximation in two simple cases. One is in a spherical geometry. If you have a point source in a kind of a spherically symmetric infinite media, this is the solution to the standard diffusion approximation. We're going to consider this in more detail later on when we talk about time domain and temporal frequency domain photon migration. And if you're not interested in the time variation, if you have a steady state source, a continuous source, if you integrate this first equation over all time from 0 to infinity, you'll get this steady state variation. So you get kind of what happens classically in terms of a spherical wave is that you get an attenuation with 1 over r, and you have this decay according to mu effective. And this mu effective is precisely what we just discussed in response to this question. It's the square root of this prefactor mu a and mu tr. Okay. And then another kind of very important one-dimensional solution is the case when you're in Cartesian coordinates, where you have a plane wave that's incident on a medium, and your one dimension is in depth. And again, here you get a modification in the prefactor and the prefactor of this equation, because you don't have this increase in surface area with z, whereas here you have this increase in surface area with r, and then you have again the steady state solution when you integrate over all time. And so here are just some definitions. We have what we find is an optical diffusivity kappa, which appears in the denominator of the time domain solution. And this again is analogous to what happens in thermal diffusion, for instance. If you look at the solution to point sources, or planar sources in thermal diffusion, you get thermal diffusivities, and they take similar. The solutions to the equations take similar form. Okay. Here you'll see that you see an identical attenuation of the light given to the optical path length, mu a times v times t. So this is actually the actual length of photon propagation, and you extinguish that. It's kind of like a Beer's law right there. Okay? Okay. So now, are there any questions about that? I'll just give that to you as a result, and again, refer you to literature if you really want to know how those are derived. So now I want to talk about a variant to the standard diffusion approximation that I think is very powerful and yet conceptually, not too difficult to grasp. So what I've done here is rewrite again the radiative transport equation, where I've already substituted in the phase function given by the standard diffusion equation. It's called the Eddington phase function. That's why there's a little e here, but it's just the same phase function we saw a few slides ago. And what we do in the delta P1 approximation is that since we know that tissue is generally highly forward scattering, and we often use directional collimated beams, we want to be able to more effectively model light distributions which display a strong forward peak, and phase functions that have a strong forward peak. So what we do now is that we say, well, let's consider our radiance, and let's just say that we decompose it into two terms. One is a diffuse term that results after the light has been scattered. And this diffuse term will retain the exact same form as what we used in the standard diffusion approximation. It'll attain that form of an isotropic term plus a cosine theta term. But we're going to also allow some fraction of light to remain collimated, because we saw in these phase functions for Mie scatterers that a lot of this light just keeps on going forward with very small angular deflection. So we're going to allow some of that light to remain collimated. Over time, the amount that remains collimated diminishes as more and more scattering occurs. And we're also going to do the same thing with the phase function. We're going to say, well, hey, let's take a fraction of this light upon scattering and keep it in the same direction of collimation. So here, the direction of collimation is denoted as omega naught. Okay, so that's your incident direction of your light propagation. And then the remaining fraction will be scattered like your Eddington phase function. But since you've peeled off a fraction into your forward scattering, the resulting G will be slightly different. It'll take on a different value because you're not taking, in order to conserve the total amount of light, the value of G here will actually need to be smaller than the value of G in the standard diffusion approximation. And that's what the power of the delta P1 is that because you're going to allow some of this light to stay collimated, the degree of anisotropy that the Eddington phase function needs to accommodate is reduced. So typically the values of G star are much smaller than the values of G. Okay? So we now take this and quote unquote dump it into the radiative transport equation, and we get the following modified radiative transport equation. This radiative transport equation is essentially identical to the one that we showed earlier at the beginning of class, only this radiative transport equation describes only the diffuse component of light. It doesn't describe the collimated component of light, and we'll take care of that in just a moment. And instead of having mu t multiplying the radiance, we have something called mu t star. Instead of mu s multiplying this scattering integral, we have mu s star. And then we have a modified source as well. So this ends up being a modified scattering coefficient, mu s star, which is the product of mu s times 1 minus f, again, f being the amount of the fraction of the light that remains collimated. And if you go through the mathematics, this ends up being sensitive to the second moment of the phase function. So here we start to get sensitivity not only to the first moment of the phase function, but also the second moment, which is helpful in some situations. We'll have mu t star as a modified transport coefficient, mu a plus mu s star, as defined up here. And then you have a modified scattering asymmetry coefficient, which ends up being the first moment of the phase function. Typically we refer to this as G just to avoid confusion with the second moment. I just subscripted it with G1. So this ends up being G1 over G1 plus 1. And then we call PE star this modified Eddington phase function because of this modified asymmetry. And then we have a diffuse source. Okay? Yes, Kayvon, we need the...
In the phase function, where you have your collimated portion that you describe, you multiply by 2. Is that to account for the fact that you don't have a 4 pi steradian normalization, or is that to weight the collimated more?
So that too comes about that the collimation occurs only in the forward direction, but not in the backward direction.
Okay.
Right. So if you actually, there's another method which is a little more exotic, which is called double delta P1, where you actually allow for collimation both in the forward and the backward direction. So you would then have two terms, a fraction of delta 1 minus the same dot product, and then you'll have one with the negative omega naught. But yeah, so this is just to do the right normalization in your spherical coordinate geometry.
Thanks.
Yeah. Any other questions? Okay. So you find that this form is the exact same form as the initial radiative transport equation, except you have these modified coefficients. And what's really powerful about that is that then actually, intuitively, if you then take the same functional dependence for LD, you'll get the same equation, ultimately, for the diffuse light. Okay? And so the delta P1 and delta P1 approximation is actually the exact same equation, except the source has a modified coefficient. And then also we need to describe how the collimated light decays as it propagates in the tissue. And that simply will decay according to an exponential of mu t star, which essentially is the attenuation of the collimated light into diffuse light. So basically this gives you the solution to the diffuse fluence rate, and then you'll add a collimated fluence rate, which is basically an exponential of minus mu t times your distance of propagation. But the key thing here is that now you have mu a and mu tr, which is sensitive to G1 or G, and then you also have the introduction of mu s star, which is sensitive to G2. So actually, the delta P1 actually provides results that are sensitive to the first two moments of the phase function. So if your measurements are sufficiently sensitive to the phase function, using the delta P1 approximation gives you a quick analytical way to actually be able to extract perhaps some information of the phase function, and more information on this is given in this paper. So these are the governing equations for both the standard diffusion and delta P1. I'll be showing some results from both. But in order to solve these, we need boundary conditions. And so I want to talk a little bit about boundary conditions. So before moving to that, any more questions about the governing equations, how they're derived, what's the underlying premise of that? Okay. So in typical situations, you're measuring light, or you're interested in delivering light in situations that you have a surrounding environment as air, and therefore you have a refractive index mismatch. And in order to solve these equations, we need to take care of the light transport at these interfaces. So here I'm just depicting a location that's meant to be very, very close to this boundary. And in general, you're going to have an angular distribution of light that's emitted from these points very close to the boundary. And I just moved it far away so that you can just depict, okay, in general, you're going to have light emitted from all these directions, and we want to see how much of that light is going to come out, and as we know, some of that is going to be internally reflected. And this is classically described through Snell's law, which probably all of you remember from high school physics, has a very simple functional relationship where the product of the refractive index, which with the sine of the incident angle, is equal to the refracted index in the transmitted medium times the directionality, the sine of the direction in the transmitted medium. So when you're going from high index to low index, essentially you get a deflection of the emitted light away from the unit normal. And you also know that for angles that are larger than this critical angle, you get total internal reflection. So for angles less than this critical angle, you get some transmitted light, you get some specular reflection within the medium. But then once you go beyond the critical angle, everything is totally internally reflected. And we need to take care of this because, again, the radiance is an angular function. And so if we want to describe the angular distribution of light, or even the amount of light close to the boundary, you have to take care of the fact that you have an angular diversity of emission, and a different amount of light actually escapes depending on the angular incidence of that light on that boundary. Okay? So just to remind you again what the functional form of this is, so the Fresnel reflection is given by this equation for unpolarized light. So we're going to just throw away polarization, since we've chatted about that the standard the radiative transport equation generally does not handle polarization, and certainly the standard diffusion approximation does not. Just want to remind you what these equations look like. So in red here, I show the angle, the amount of internal reflection one gets depending on the angle of incidence. And it's fairly flat. It's fairly very, very low magnitude until you get very close to this critical angle. And then, of course, at the critical angle, everything is reflected back in. And then here we get transmission. So essentially, if you're far away from the critical angle, almost everything that impinges on this boundary gets transmitted, except once you get kind of beyond 30 degrees of angle of incidence, then you start to get a dramatic fall off, and then obviously beyond the critical angle, nothing gets out. And then this green curve essentially shows you the relationship between the angle of incidence and the angle of transmission, okay? And so initially it's fairly linear, and then you get this little curve. So you get an increased deflection to the outer, away from the unit normal as you get closer and closer to that critical angle. So somehow we need to embed this angular mapping of of the radiance that resides within the medium at z equals 0 plus to the radiance that emerges from the tissue boundary, okay? And so let me just tell you how Monte Carlo does this, because Monte Carlo does this completely faithfully to the physics. So one way one can do this is that if you have a photon that is being emitted from some scatter or scattering interaction and starts to travel towards the surface, it has a given weight W. So say we're using one of these weighted Monte Carlo methods, such as continuous absorption weighting or discrete absorption weighting, as opposed to analog. We could say, hey, it's impinging on this boundary. We know a fraction of it based on the angle of incidence is going to be reflected back in, and the remaining amount of that weight will be transmitted. And so one can do that. One can just say, okay, I'm going to split this photon into two photons, where I'm going to let a fraction of that weight escape, and if there's a detector here, we can tally that weight. And then we'll continue the propagation within the medium with a reduced weight that's equivalent to the Fresnel reflectance that's appropriate for this angle of incidence multiplied by the weight before that reflection. So that's one way one can do it. Another way we can do it is that, well, we don't want to, if one doesn't want to split these photons into two photons, one can do what's called a roulette. And here what we could do is that we could just say, let's throw a dice, a random number between 0 and 1. And we say, well, if that number ends up being between 0 and the Fresnel reflectance, we're just going to essentially reflect all of that, that whole photon back in. If that random number is between the reflectance, Fresnel reflectance, and 1, we'll transmit that whole photon. And statistically, over thousands and thousands of trials, both of these methodologies will converge to the same result. Okay? And it really just depends on the various metrics that you might be interested in that may benefit one methodology over another. Okay? Any questions about this? What I want to emphasize here is that Monte Carlo has the ability to do a detailed balance for every single angle, or for any angle of light impinging on this boundary, right? So the Fresnel reflectance will take on a different value depending on the different angle of incidence on that boundary, okay? And this is not going to be able to be achieved using these analytical approximations, okay? So in the standard diffusion approximation, we can't do this. And what we do is that we do what's called a hemispherical balance. So what we do is that we say, well, I can figure out all of the light, I can calculate all of the light that comes down back into the tissue, traveling in directions in the hemisphere corresponding to positive z. So this is an integral over all directions in this forward hemisphere of the radiance. So this is all of the light that is traveling down from that boundary. at z equals 0 plus inside the tissue. And that light coming down has to be equal to the light that has traveled up. So z dot omega is less than 0. So this is all of the hemisphere pointing upwards. At z equals 0, that gets reflected back down. So this represents all of the light that is close to this boundary, z equals 0, that is traveling upwards, because we're looking at the dot product of z with omega, which is less than 0, which means that it's traveling against the inward pointing unit normal. We take all of that light and we multiply it by the Fresnel reflectance according to that angle, and we integrate over all angles in the upward hemisphere, and that has to equal the light coming down. Okay, so this does a balance only. It does what's called a hemispherical balance, right? You're not doing a detailed balance angle by angle, but you're doing a balance over all angles. And then what we can do is that we can approximate this by putting in our radiance approximation. So whether it's a delta P1 approximation or a standard diffusion approximation, this L will be substituted in as a sum of a delta function plus an isotropic term plus a first order anisotropic term, the cosine theta term. And if you do that in the standard diffusion approximation, you get this boundary condition here, which for those of you who are familiar, this is known as a mixed condition because it has both the fluence rate plus the derivative of the fluence rate with depth, the gradient of the fluence rate. And it's a homogeneous mixed condition or a homogeneous Robin condition. Okay? So any questions on this? Do people kind of understand kind of the trade-off we're making, or the additional inaccuracy one imposes in some sense in simplifying the boundary conditions in this case relative to what's happening physically? Are people following the kind of the concept behind this math or not? Yeah, Kevon. So let's ask questions. Don't be shy.
So just to be clear, the left side of the equation,
yes,
the radiance going out of the slab?
The radiance coming down. So we're only considering in this boundary condition the light that's inside the medium, right? Okay. That is our medium where we're solving. This is the light that travels down from this interface down into the tissue. And that's denoted by this z dot omega greater than 0. So this is a dot product between the inward pointing normal, and omega represents the direction of light propagation. Mm-hmm. So that will only be greater than 0 for all, basically from 90 degrees to 0 to minus 90. Okay, so this refers to the integral of your radiance for everything in this downward hemisphere. Okay? So we're saying that the amount of light that comes down from that boundary into the tissue is equal to the light that actually travels upward, because now we have this dot product less than 0, that then gets reflected. Right? So you take all of the light that is traveling upwards. Of course, some of it is going to escape, right? So not all of it is going to be available to then travel downward. We have to multiply it by this fraction. That fraction is going to be dependent on omega, right? Because it's dependent on the angle. And then you integrate that over the whole upward solid angle space. And that has to equal this, right? Mm-hmm. So the stuff that comes down is the stuff that goes up and then gets reflected.
And it's only a fraction of that.
RF is always a number that's between 0 and 1.
Okay.
Right?
Yeah. Okay. Thank you.
Yeah, sure. Other questions? Okay. Okay, so I just want to, so essentially this refractive index mismatch introduces a discontinuity in both the magnitude and the angular distribution of the radiance. And so one thing I just want to emphasize is that when you go from in some sense, a cone of light that is impinging on the boundary, if you're going from a high refractive index to a low refractive index, light that occupies a certain solid angle gets distributed over a larger solid angle after it passes through that refractive index mismatch. It basically diffuses the light. And of course, light that essentially is just below the critical angle basically will skim the surface of the tissue. So essentially, it's only light from theta equals 0 to the critical angle which will give rise to a completely hemispherical distribution of light on the other side of that boundary. Light that travels upwards from angles greater than the critical angle, of course, get totally internally reflected and do not contribute to the light that emits. Okay, and here are the equations that relate the light that's inside the tissue to the light that's outside the tissue. Okay, and that's relevant when you have to determine reflectance. Okay. So that's kind of the theoretical foundation of how one can extract metrics for fluence rate and ultimately reflectance, which we'll talk in more detail later. Now I want to talk about sources and how we can parameterize internal fluence rate, because as I said, the focus of this lecture is really on internal fluence distribution. So going back to kind of this figure that I showed on day one, what I want to consider is, number one, looking at distributions of light within the material. And there are kind of three standard sources that one can consider. One is kind of a very narrow collimated beam, a pencil beam, often referred to. And here this will establish some sort of distribution of fluence rate, which is again the integral of the radiance over all 4 pi solid angle with depth. In reality, often, especially for cases of dosimetry or fluorescence excitation in bulk tissues, one doesn't use a pencil beam, but one uses a beam of some finite diameter, which is of dimension that is comparable to your typical scattering lengths or absorption or absorbing lengths, and therefore one has to model explicitly the finite size of that beam. And then in some cases, say in photodynamic therapy, for instance, often one uses very large beams because you want to maximize penetration. And so in the limit of a very large beam, one can model this as a one-dimensional wave impinging on a tissue. Now, depending on your application, one might be interested in different metrics for how far this light penetrates within your tissue. And so I'm going to define two different metrics, and I'm going to define these dimensionlessly. So I'm going to use the Greek capital pi to refer to the depth in the tissue at which the fluence rate falls off to 1 over E of the incident fluence rate. So I'm going to call this a penetration depth. So this is relevant. Say you have a minimum intensity that you want to achieve in the tissue, either to excite a minimum temperature change or to excite a minimum level of fluorescence, or you have some threshold intensity you want to achieve. And this will give you an idea of how that depth will change with optical properties or with the beam diameter. Another relevant metric is what I'm going to call the dose depth. Sometimes you want to know where is most of the energy of that light field absorbed, okay? And so there you're not interested so much in a minimum intensity, but you're interested in the integral of this and where is most of that light absorbed. So I'm going to define a depth called capital delta, which denotes dose depth, that essentially tells you the depth in which basically 2/3 of the light is absorbed, all but 1/e of the light is absorbed. And you'll find that actually these two parameters actually have slightly different functional behavior. Okay? And these are very useful scalar metrics to evaluate the spatial extent of these fluence distributions and how these vary with optical properties. So one thing I want to emphasize is that in the case of a purely absorbing tissue, so say we don't have scattering, in a case of purely absorbing tissue, pi will end up being 1/μA, right? Mu A is the absorption coefficient. The Beer's law is exponential of minus μA times z, right? So this would just be 1/μA. And it ends up being also 1/μA for the dose depth. So in the case of complete absorption, both of these metrics will be 1/μA. Okay. In the cases of complete scattering, they attain different values. So what I'm going to be showing you in a bit is just to give you an idea of how scattering affects these penetration depths. And often, something that is often bandied about in the literature is how this parameter here, which we've already written up on the board, how mu effective in cases of high scattering, the reciprocal of this is often referred to as a penetration depth. And for diffuse light, sometimes is. And that has some validity, but as we'll see, I'll call this is kind of often referred to as a diffuse penetration depth. But it does have some limitations. Is there a question back there, Jerry? Is there a question, Jerry?
Well, there was a question, but Gordon decided to hold it for
I think it's worth it raising.
It relates more to, my question related more to the previous slide.
Okay.
So, and it was really a general question. So when you talked about what gets reflected and transmitted at the critical angle or
Yeah.
generally out of tissue, you're assuming a smooth interface.
Of course, yes.
And I guess most tissue's rough, and so these angles are different.
Sure.
How do you account for that?
We don't. Right? So that's another limitation of this often, and I actually am not really that experienced in understanding those issues. I do know that in some applications we use index matching agents on the surface of the skin. And, certainly I know in the integrating sphere measurements one will be making, often there is a thin layer of fluid that's put between the glass microscope slide and the tissue to kind of mitigate, to approximate that flat boundary. But you're right, in reality you have this microscopic undulating surface. That's the reality of what happens in tissue optics.
I was wondering if it kind of falls out because you then effectively have a distribution of incidence angles as you go along.
Yes.
And depending on the roughness you have, that distribution could, go from, if it's smooth, to essentially a very small distribution around the angle at which you hit
Sure.
it, to if it's rough, a very large distribution, and if that's
Right.
just another probability distribution that you have to sample.
Yes. It would be interesting to do an experiment where you actually just vary the angle and see if it's and calculate what would be the amount of light coming out given, say, an isotropic source right below the surface, and see if the amount of light that escapes or doesn't escape, is it always one-sided, or is it go above or below the mean value? Intuitively, I think it might be one-sided, so there may be a bias that may occur as the surface gets rougher and rougher. But I don't know for sure. I'm just kind of saying something off the cuff just from complete intuition. I think Tom may have a comment. Let's bring the microphone over. And then obviously the people from Circuit Core who live this probably may know something about this.
Yeah, some of the tissue, like with skin, okay, you're going to have very small changes, like on the arms and most of the body. But if you're coming out of the hand, these are some rather large ridges which are going to really spray the light around.
Sure.
And that would be interesting to see. That might actually be something where you can take an imprint and then embed it into the simulation, perhaps.
Sure.
Because these are going to be varying around, I think, a few hundred microns are the
Sure.
ridges that you're going to get on the
Right.
fingerprints.
I do know that in people who do spatial frequency domain imaging, often because they have these patterns of light, they can image those patterns of light and see how much they stray from being straight when they image that, and that actually maps onto the angular variation of that surface, and then they can correct for that when they measure the reflectance, because it has the same issue that we discussed on day one when I think Tom was asking the question of where does that dot product come from when you transform the radiance to the reflectance. Remember, and you're saying that as the light comes out at an oblique angle, you're spreading light that emits from a small solid angle onto a large surface area. And it's the same sort of thing that occurs here, that your reflectance may get modified, reduced, and you have to correct for that cosine theta term. Any other questions? Kevin.
I have two questions, but about your next slide.
Okay.
So the penetration depth. So the term we have on the board and the other two types of depths that you define, how close are they? Even closely related?
We're gonna have some results that
Okay.
we'll talk about that in detail.
And
Actually.
then secondly, for any of these descriptions of depth, can they be converted such that you say, I don't know, let's say for penetration depth, instead of it's 37% of my fluence rate that reaches this depth, can I say that it's 37% of my photons that have reached this depth?
No, I wouldn't say it's 37% of your photons that have reached this depth. It's just that the local intensity is 37% of the incident intensity.
So I'm wondering, is there a way to go from this to actual number of photons?
Well, that's this, right? Because here you're integrating all your photons here. So that's the dose depth, right? So here, all but 37% of your photons have been extinguished within this depth.
Okay.
And the remaining is below that depth.
Okay.
Yeah.
Right.
So,
Thank you.
yeah, sure. Mohit, you have a question there.
Why do we see the maximum intensity a little below the surface and not like very like at the surface?
We'll talk about that in just a moment. Yeah, and it doesn't always happen, but it does happen. Yeah. Just real briefly, it's because you have a leakage of light from the surface because some of the light that gets there escapes. So you have a loss of light. It's kind of like if you're a heat transfer person, I think you have a flux. You have a loss of heat. You have a heat loss. Here you have a light loss from the surface. So just like you may have a maximum temperature just below the surface, you have a maximum photon density on the surface. So it depends on how much loss you have. Yeah. Okay. So let's go forward. So here I already mentioned this, kind of in the governing equation of the standard diffusion approximation provides a natural spatial decay rate for the fluence distributions. It's essentially linked to mu effective, or the square root, it is linked to mu effective. And in the standard diffusion approximation, we also have a natural length scale, which is linked to the decay of light in the tissue. And typically in the standard diffusion approximation, the laser irradiation is often represented by a point source that's either embedded a transport mean free path below the surface, or sometimes as a distributed source, which decay as minus mu tr. Again, this is the reciprocal of the transport mean free path. And so this will introduce another intrinsic spatial scale, because that spatial scale is the the length over which that source will decay. In the delta P1, this mu tr will be replaced by mu t star, which again is mu t times 1 minus f. So here again in the delta P1, mu effective stays the same, but the source will have a different decay rate, okay, which is actually sensitive to the second moment. Actually, the whole source ends up being sensitive to the second moment. Okay, so we'll get to depths in just a second. So I'm going to show a series of results now. So what I'm going to plot here is the fluence rate as a function of depth. The depth is going to be normalized to this transport mean free path, again, which is the reciprocal of the sum of mu a and mu s prime. Here I'm going to consider a fairly strongly scattering tissue. The ratio of reduced scattering to absorption will be 100 here. And then these subsequent plots are for increasing absorption. So here that ratio is 10, then 3, then 1. The isolated symbols are results from Monte Carlo simulations that we've run. And we've run enough photons such that the precision or the variance of these results are smaller than the size of the symbol. And you can kind of sense that because all of these results, they look very, very smooth. Okay, so we've run enough photons. And we're considering a case where refractive index is matched. So where there's no refractive index mismatch at the boundary. So we see something that's interesting. So here, again, when you have lots of scattering, you have lots of light that's being scattered back to the surface. And actually you see this subsurface peak, as Mohit just asked about. And then in the far field, you see kind of an exponential decay. This is a log y-axis. So a straight line here means an exponential decay. Okay? And actually, the slope of this exponential decay is equivalent to mu effective. So that's kind of the spatial decay rate. As you increase absorption, mu effective will increase, and therefore you get a more aggressive attenuation. You have less backscatter back. This slope close to the surface goes down because there's less reflectance. And then, of course, when you have more and more absorption, the decay happens more rapidly. You get less of the subsurface peak. There's less light coming back out. Okay. Now, remember, when your refractive index is matched, relative refractive index is matched, all light that comes back out through that top surface will escape, right, because your index matched. So now I'm going to show the result when you change the refractive index from 1 to 1.4. So how do you imagine the result may change? So before I show the result, any thoughts as to how this might change? Yeah, so hold on,
I would think that less light would escape on the way out.
Okay.
Light leakage.
That may be the case, but we're actually looking at the internal fluence distribution. So how might the internal distribution change? So if less light escapes, that means that what would have to happen to the fluence distributions? Since photons have to be conserved. Yeah, the overall amount of light you'll have inside the tissue will increase, right? Because some of the light that wants to come out ends up being reflected back in. And you'll also get a slight enhancement in the penetration, right? Because not all the light can come out. But that's, okay, so, and that's what we see. But we see this more so in the case where there's lots of scattering, okay? So here, in the case of mu s prime or mu a, 100, that's where you're going to have the most reflectance, and therefore there's more light available to be reflected back in. And you see that the slope actually is smaller, which means that, as you correctly stated, there's more light, less light leaking out, more light leaking in, and you get a general elevation of your fluence rates throughout. But as you get more and more absorption, the differences between these two results diminish. And they diminish because there's less light that gets backscattered out and to try to escape. And so you get a less elevation. And in the case where you have, almost all absorption, you get essentially the same result. Okay? Okay, any questions on this? Yeah, so Josh, 1 second.
Is that only the case because you have the depth z over L star? Because as you increase n, then you would shorten the mean free path. And so you get
Say that again,
scattering.
as you increase what?
N, then your mean free path shrinks, right? Because then particles are closer together.
Okay, so sorry, I think I wasn't clear. So these n's do not refer to the refractive index of the particle. They refer to the mean refractive index of the medium. So the reason why I'm showing these two n's is to juxtapose a case where you may have tissue in an aqueous environment where basically, roughly the refractive index mismatch at the boundary is minimized versus a case where you have tissue in air. But I'm not changing the relative refractive index of the scattering particles within the medium. So in that way, your transport mean free path is exactly the same in all of these simulations.
Okay.
Okay? Does that answer your question?
Well, if you change the average, don't you change the particle?
No. So we're changing the background. So here, I guess maybe I should say this is the refractive index mismatch between the tissue and the surrounding medium.
Oh,
Okay. I'm sorry if I didn't make that clear.
that makes sense. Because
okay.
you can change like the outside.
That's right.
Yeah.
Right. So like in microscope objectives, sometimes you have oil immersion lenses because they want to better match the tissue with the objective lens so that they get as much light out as possible versus an air objective.
And then is there a purpose for doing z divided by L star? Or?
Yeah, that just puts the spatial scales for, I have different sets of mu A and mu S prime for each of these. And so you want to have a characteristic length scale which is representative of light transport in all of these systems and have that uniform across. Okay. Otherwise, if I say increased, just imagine one way of going from mu S prime over mu A from 1 to 100 was to keep mu A fixed, but increase mu S prime by a factor of 100. But if that's the case, your transport mean free path will be reduced by 100 times. Mm-hmm. And so then this plot, everything will be between 0 and this first tick mark, and the other one would be extending all the way. But that's because you've fundamentally changed the physics, the characteristic length scales in the problem. So you want to have that length scale conserved across all your simulations.
Do they usually use that? Because I've seen it just like with depth.
Yeah,
so
right. So that's misleading, I think, when you do that. If you want to make comparisons with respect to, ultimately everything should be normalized to a characteristic length scale of the physics.
Okay.
And the characteristic length scale of the physics, the interaction of light with tissue in the diffuse regime is characterized by L star, which again, just to remind you, is L star is equal to 1 over mu TR, which is equal to 1 over mu A plus mu S prime. Okay.
Thank you.
Yeah.
Just one quick question. So when you say fluence rate, the units that you're using is like watt per unit?
So fluence rate, the actual fluence rate is, watts per meter squared or watts per millimeter squared. It's a irradiance.
Okay.
Right? It's like an irradiance, but in a spherical sense, right? Because you're looking at total amount of light emitted from a point. Okay, and it's just normalized. So I have an incident fluence rate of 1.
That's right, all the units.
Yeah. Okay. Any more questions? Okay. Okay, so these plots show what the lines show what the standard diffusion approximation provides. And you see that in the high scattering case, you actually do very, very well far away from the boundary. You identically capture the appropriate decay rates. But starting about 2 mean free paths from the surface, you start to see deviations, and significant ones. And that's primarily because of the fact that it doesn't handle the boundary very well due to those hemispherical integrals, which represent approximations to the boundary conditions, to the escape of light here. And so there are errors that are made there. And as you get more and more absorption, actually things get worse and worse, because once there's more and more absorption, these light fields become more and more asymmetric, because you have this very highly forward-directed collimated light. You don't have that much scattering, so this assumption that you have essentially an isotropic field plus a first-order kind of cosine theta term starts to really fall apart. And in fact, once you have high absorption, you can even see that the decay rate of the true light field is not predicted properly at all. And you can see this just intuitively because, again, far away from the boundary, the standard diffusion approximation will introduce a decay rate which is essentially 1 over mu effective. In the limit of mu s going to 0, so in the limit where you have complete absorption, mu effective ends up being the square root of 3 times mu a, which basically gives you Beer's law on steroids, right? Because it's off by a factor of 1.7. So the attenuation rate is too rapid, and it also, does poorly in the boundaries. And so this can all be corrected for quite well using the delta P1, because the delta P1, whose results I show here, provide for this. Assume that you begin with collimated light, and that as it gets scattered, it populates the diffuse light, and then you do a sum between the collimated term and the diffuse term, and actually you recover the light fields quite well, even in strongly absorbing cases. Because in the absorbing cases, your collimated light field persists much more deeply into the tissue, and your diffuse light is actually very, very small, and this is representing the sum of the two. So with that small change, you actually can reap big rewards with respect to the handling of internal light fields. Okay? And so these errors are less than 10%. So here I want to go to this results for penetration depth and dose depth. So this is a little complicated slide, but it has a lot of information. So what I've done on the y-axis here is that I've plotted the physical optical depth and multiplied it by mu effective. So mu effective is in units of inverse length. So this is dimensionless, okay? And on the x-axis, I've plotted the ratio of reduced scattering to absorption, okay? Going from basically purely absorbing to very, very highly scattering, okay? And the symbols, again, here are Monte Carlo simulations. I've shown both cases where you have refractive index matching between the tissue and the surrounding media, and a typical refractive index mismatch. The open symbols here are the penetration depth, the depth at which you fall to 1 over E of the incident depth. And delta here is the dose depth, the depth at which all but 1 over E of the light has been absorbed. So you see at the case where you have basically pure absorption, all of these values converge to essentially the square root of 3, right? Because you know that mu effective gives you the square root of 3 times mu a, and you have to get rid of the square root of 3. The true optical depth is 1 over mu a, okay? So this is essentially square root of 3, because the true optical depth is mu a. Oops. Is mu a, and mu effective in the limit of no scattering ends up being, end up being square root of 3. Sorry, hold on. Am I doing this right? Let's see. So optical depth is 1 over mu A. And then mu effective is the square root of 3 mu A. Right, so this goes away and you get that. And then what's interesting is that for high scattering, the dose depth ends up being equal to 1, which means that essentially the optical depth is essentially mu effective, which is what you would expect from diffusion. Okay, so it does very, very well for high scattering, but you start to see that you get deviations from that. The penetration depth is actually much larger, and that's primarily because you get the subsurface peak. So if you notice these curves, even though my incident field has an incident fluence of 1, you actually get peaks that are multiple times of that because of that backscatter of light coming back. And so the penetration depths are actually multiples of mu effective. And of course, the penetration depth is much higher when you have that refractive index mismatch than when you don't. If you predict these using standard diffusion, again, you do not so badly for this penetration depth. You don't do very well for this dose depth. And then, of course, when you go to delta P1, you actually do some quite well. And across, from highly absorbing to moderately scattering to highly scattering, you recover these depths very, very accurately. Okay? Okay. Any questions on that? So this is a really kind of powerful chart because if you know the mu A and mu S prime of your medium, you can then just look up the value on this chart, and then you get the physical, you read off your value, you multiply it by your known, or you divide it by your known mu effective, and you actually get the physical optical depth. So this plot is general for any set of optical properties, and you can read off your depth. Kayvon.
So when would you use the optical depth versus the dose depth?
Well, like I said in the beginning, if you're interested in the depth in which, say, most of your light is absorbed, so say you want to do a photothermal therapy, and you're really interested in how is, say, the volume of material I'm going to coagulate, how might that change based on changes in the optical properties of that tissue? I probably want to look at dose depth, right? Where is my light going to be absorbed? Because that's going to create the temperature change. Mm-hmm. If I know that I have if I'm, say, doing a photodynamic therapy treatment, and I know that I'm going to activate this dye for all irradiances greater than a certain level, then I don't care so much about where the majority of the energy is absorbed. I'm worried about how deep am I going to attain that minimum intensity of light to activate that dye. In that case, I'm probably more interested in the penetration depth and how that might change with optical properties.
That makes sense. Okay, thank you.
Any other questions? Okay.
Is this
Yes, sure.
independent of the beam diameter?
No, this is all for
A fixed beam?
This is for a large one-dimensional, so large beam diameter. And so I'm going to talk about beam diameters just now. Okay. So here I'm going to show the effect of beam diameter. So here's results of the fluence rate versus depth for beam diameters of different radius. So here I've scaled the beam radius relative to this transport mean free path to give us a general set of results. This is for highly scattering medium. And here I've just shown the delta P1 approximation since it does much better. And you start to see, of course, that you get, since you have as you reduce your beam size, you get losses laterally. This is along the center line of that beam. Okay, so this is at r equals 0, so we're looking just in the center of that beam. And how the fluence rates degrade with depth. And you see, obviously, when you go to a beam that's, very, very large relative to the transport mean free path to one that's maybe comparable, so this would be, say, a 1 millimeter beam impinging on tissue. This would be a 100 millimeter beam, 10 centimeter beam, 4 inches in diameter. You have a factor of 4 drop off in that fluence rate right at the surface. And of course, even larger drop-offs deep into the tissue, okay? Because again, you're losing light laterally due to dispersion, okay? And again, the symbols are Monte Carlo and the lines are the delta P1. Now, when you're in lower scattering media, you don't here, this is mu s prime or mu a of 1. The impact of beam diameter is far reduced, right? In the limit where you have no scattering, it doesn't matter whether you're using a broad beam or you're using a pencil beam, right? Because there's no scattering. You just have penetration according to Beer's law. Okay, and you see this even though you do have some scattering here. Actually, you have equal amounts of absorption and reduced scattering. You do see the impacts of absorption. And you see actually the delta P1 doesn't do that great. Here, and that's because again, now we're approaching spatial scales comparable to L star, and these you start to approach what's known as the transport regime, which Dr. Spanier talked about in his lecture. That in general, all of these diffusion approximations are really relevant in cases of very, very high scattering, and here where you have comparable ratios of reduced scattering and absorption, and you're on spatial scales comparable to the transport mean free path, you start to get failures in that approximation. Okay, so the delta P1 most definitely has significant limitations as well, but it does mitigate a lot of the problems of standard diffusion. You'll have all of these. I think I won't get into these so much, but these actually give you these penetration depths for beams of a finite size. So the first one was for beams of infinite extent. This gives you optical penetration depths for beams of finite extent. And this is the dose depth for also beams of finite extent. So these are kind of really practical, helpful charts that one can use to estimate these parameters. And these, I don't want to take too much time because I want to get to slabs and then wrap up. Okay? And then these are some figures of how the actual distribution, those plots were just along the center line. These plots are the actual full distributions, and I think the solid lines, solid curves are Monte Carlo, and the dotted curves are the delta P1 approximation. So you can see the fact that they match up quite nicely means that it's doing fairly well. This is for highly scattering media. This is for low scattering media. So I just want to talk very briefly about slabs because that's what's going to be the topic of the next lecture. And this is very important for optical analysis of excised tissue samples. And the analysis that I'll show you here can provide the internal fluence rate distributions as well as the reflectance and the transmittance. So in reality, so we can not only get the internal fluence rate, which is going to be a function of mu s, mu a. Actually, when the slabs get very thin, it's going to be sensitive to G as well. And of course, the thickness of the slab. And so the fluence that's available at both the proximal surface as well as the distal surface will give us reflectance and transmittance. So here, I just want to draw your attention here. So here on the x-axis is a normalized depth. So Z is normalized relative to D, which is the thickness of that slab. And we're looking at slabs of different thicknesses from 1 L star, which is roughly a millimeter, to say 12 L stars, 12 millimeters. So even though this red curve goes from a fluence rate of 3 to a little bit below 3, remember this whole span for this black curve refers to only a span from 0 to 1 L star. Whereas for the red curve, this span from 0 to 1 refers to a span of 12 L star. Okay? So you don't match this point with this point because it's actually the spatial scale is much less. So here you see that for a very, very thick slab, you start to see a significant spatial decay. You have a lot more light available in reflectance, a lot less light available for transmittance. As that slab thickness goes down, you start to see a reduction of light available for reflectance and more light available for transmittance. And also, as the slab thickness goes down, the absorbance will reduce as well. And so actually, if you add reflectance and transmittance for the thinner slabs, that sum will be larger than for the thick slabs, because in thick slabs you're going to lose more to absorbance. Okay? So here, increases in slab thickness increases the fluence rate near the front surface. You get higher reflectance, but less transmittance. And then here, I just show you what happens if you have refractive index matching. Refractive index matching, again, you're going to have a drop in the reflectance. Your fluence rates are lower here. You actually have some drop in the transmit. Well, you actually don't necessarily have drop in transmittance, and you have less absorbance. And so we'll see the reflectance and transmittance in just a second. And then here, I'm showing plots for more highly absorbing situations, where again you have much more extinguishing of the light field for the thick tissue slabs, less so for the thin tissue slabs. And again, when you have the refractive index mismatch, you see a shift. So this gives you an idea of how reflectance will change with slab thickness as you increase in scattering. Again, as you increase in your slab thickness, you'll get more and more reflectance for more highly scattering materials. And this gives you the change when you have a refractive index mismatch. Your reflectance tends to increase for the highly scattering, for the thick slabs. And then we also have plots for absorbance. So what you're going to end up doing in your lab, and Dr. Sagar will explain this further, is how you can relate measurements of absorbance, of actually reflectance and transmittance, not necessarily absorbance. Absorbance is what remains from reflectance and transmittance, and convert those to absorption and reduced scattering properties. Okay? So I think I'm going to end it there. I have a summary, which I'll just put up here. So essentially, we talked about standard diffusion and delta P1 approximations, how they're formed analytically, how they reduce the radiative transport equation into partial differential equations that can be solved. We talked about how Monte Carlo handles the refractive index of the mismatch of the boundaries rigorously on a photon by photon basis in accordance to Fresnel relations, whereas both diffusion and delta P1 solvers handle this mismatch by enforcing energy conservation globally using a set of hemispherical integrals. We showed that increases of refractive index mismatch enhance total internal reflection, increase the fluence rates proximal to the surface, and increase penetration depth within the tissue. We showed that the standard diffusion approximation provides poor predictions for internal fluence rates at optical depths and optical depth for optical penetration depths for ratios of scattering to absorption less than about 30. Delta P1 provides improved predictions for internal fluence rates and optical depth, certainly for the large beam diameters. Predictions tend to break down for small beam diameters and for values of absorption comparable to reduced scattering. And then, of course, finite beam diameters further reduce optical penetration and dose depths, especially in highly scattering media. So I'll end it there. It's been a long lecture. I'll open it to questions, and then we'll have our break. Okay? Any questions? Yes, Tom.
I'm going to assume that when you talk about internal reflectance into the tissue exiting, you're saying internal reflectance all the time. And when you're talking about reflectance from a beam, you're talking about what comes through the tissue and is.
That's right, yeah. Total internal reflectance is, yeah.
Okay.
Yeah, that's right. Okay. Yes, please.
The depth, I guess the fluence profile that you're looking at as you drop the scattering versus the absorption, or raise the absorption for the scattering. If you were to look at this fluence profile, this would be substantially narrowed.
You mean
An increase in absorbance.
you mean the lateral? The lateral, yes.
The second moment of the fluence profile would be narrowed.
The second moment.
If it's a bivariate profile, like a bivariate.
You're talking about the radial profile. Is that what you're saying?
Yeah.
Okay. Oh, the radial. Okay, I wanted to make sure you meant radial rather than
So this
depth.
will be basically spiked as absorbance rises.
Yeah, sure. You're not going to get as much lateral dispersion due to scattering as absorption increases. Absolutely. And I'm just trying to see if we can.
I just remember that figure right there. I thought I would see that.
Well, you do. So it's a little misleading because even though the color map is the same, the values are different. So you see, this goes from 2 to 1 to 0.6 to 0.3. Here you're going from 1 to 0.3, 0.1, 0.3. So it is much narrower in this case. Here you're already 4 orders of magnitude lower. Here you're only just 1.5. Yeah. Yes. Yeah, they're not on the same scale. So I apologize for that. Kayvon.
Just going back to your summary, can you
Yes, sure, 1 second.
Do you mind just reiterating the major component that provides that difference in predictions between the SDA and the delta P1?
You mean this?
Yeah.
Okay.
Between the 2 points, yeah.
Yeah. So conceptually, remember, SDA has a hard time when the radiance distribution is highly anisotropic. And that is going to happen when there's low scattering. Because when there's low scattering, and you have a collimated beam, certainly close to the surface, your light field is highly forward directed. If you were to kind of just imagine in your mind's eye how this light field would look like, you got this collimated beam coming down, and even though you may have some backscatter coming up, I bet you if you looked at the radiance here, it's going to look something like this. There's going to be a little light coming back, but a lot of light's coming forward. Okay? And yet you're trying to approximate this by a sum of an isotropic term plus a cosine theta variation. It just can't handle it. Whereas what you do in delta P1, so in SDA, you say that this is equal to something like this. That's isotropic, plus something that's, actually it's plus something like this. Okay, that's what a cosine is, where it's positive here and negative here, right? Whereas in delta P1, you say that this is equal to, actually I want to be correct, because it should be like this and like this, right? So it's negative here, positive here, right? Whereas in delta P1, you say that this is equal to something forward plus this. Plus this. And so the amount of anisotropy that gets dumped into this component is relieved by the fact that you still have a delta component there. And so that helps you a lot. The other thing that I didn't make so clear on the slides is that in the delta P1, this fluence rate is equal to a diffuse fluence rate plus a collimated fluence rate. Okay? And I provided the equation for the diffuse fluence rate, and I gave you the governing equation, but I didn't make clear that this collimated fluence rate, say in the case of a collimated beam going down, takes the form of exponential of minus mu t star times z. Okay? And mu t star is mu a plus mu s star, and mu s star itself is equal to mu s times 1 minus f. So in the limit where you have no scattering, the diffuse fluence rate goes to 0, and all you're left with is the collimated fluence rate. And since mu t star is mu a plus mu s star and there's no scattering, you recover Beer's law. So that's how delta P1 actually accurately recovers Beer's law in the limit of no scattering, and actually does very well in regions of intermediate, just comparable absorption and scattering. Okay. Okay. Is that, okay. And I think, Josh, did you have someone else? I thought, no? Mohit? No. Okay. Okay. So let's take a break, stretch, get some caffeine, and we'll continue, 10:30.
I think there are 3 of you that have the small white and blue parking permits. And you are 2 of them. Who's the other one?
Okay. Where do we?
You haven't been using it. Okay. I need to talk to the 2 of you, that everybody else is fine. First one.
Stop.